Geometry of the linear discriminant. Two classes. Let us start with the simpler case of two classes. In such a case, one discriminant function is sufficient. G of x equals to g1 of x minus g2 of x, and which is equals to, if we expanded the term by definition, w1 transpose times x plus w1 0 minus the results of w2 transpose times x plus w2 0. If we take out x and combine the terms, that will be w1 minus w2 to the transpose, then times x, plus w10 minus w220, which is equal to w transpose times x plus w0. And we choose c1 if g of x is greater than 0. We choose c2 otherwise. This defines a hyperplane where w is the weight vector and w0 is the threshold. This later name comes from the fact that the decision rule can be rewritten as follows. Choose c1 if w transpose times x is greater than minus w0, and choose c2 otherwise. The hyperplane divides the input space into two half spaces. The decision region R1 for C1 and R2 for C2. Any x in R1 is on the positive side of the hyperplane, and any x in R2 is on its negative side. When x is 0, g of x is equals to w0, and we see that if w0 is greater than 0, the origin is on the positive side of the hyperplane, and if w0 is less than 0, the origin is on the negative side, and if w0 equals to 0, the hyperplane passes through the origin. See figure 10.1. Take 2 points x1 and x2 both on the decision surface. That is, g of x1 equals to g of x2 equals to 0. Then w transpose times x1 plus w0 is equal to w transpose times x2 plus w0. If we combine these two terms, that will be equals to w transpose times x1 minus x2 is equals to 0, and we see that w is normal to any vector lying on the hyperplane. Let us rewrite x as Duda-Hart and Stork in 2001, that is, x equals to xp plus r times w divided by the norm of w, where xp is the normal projection of x onto the hyperplane, and r gives us the distance from x to the hyperplane. Negative if x is on the negative side, and the positive x if x is on the positive side. See figure 10.2. Calculating g of x and noting that g of xp equals to 0, we have r equals to g of x divided by w norm. We see then that the distance to origin is r0 equals to w0 divided by w norm. Thus, w0 determines the location of the hyperplane with respect to the origin, and w determines its orientation. Multiple classes. When there are k greater than 2 classes, they are k discriminant functions. When they are linear, we have gi of x conditioning on wi and wi0 equals to wi transpose times x plus wi0. Figure 10.3. In a linear classification, each hyperplane hi separates the examples of Ci from the examples of all other classes. Thus, for it to work, the classes should be linearly separable. Dotted lines are the induced boundaries of the linear classifier. We are going to talk about learning later on, but for now we assume that the parameters wi, wi0 are computed so as to have gi of x conditioning on wi, wi0 equals to greater than 0 if x is in Ci, equals to less than equals to 0, which means the negative number, otherwise, for all x in the training set. Using such discriminant functions corresponds to assuming that all classes are linearly separable. That is, for each class Ci, there exists a hyperplane hi, such that all x in Ci lie on its positive side, and all x in Cj, j not equals to I, lie on its negative side. See figure 10.3. During testing, given x, ideally, we should have only one j of x, j equals to 1, 2, 3 until k greater than 0, and all others should be less than 0, but this is not always the case. The positive half spaces of the hyperplanes may overlap, or we may have a case where all gj of x is less than 0. There, these may be taken as rejected cases, but the usual approach is to assign x to the class having the highest discriminant. That is, choose Ci if gi of x is equal to the maxima of j of x, where the maxima is taken among j starting from 1 to k, and remembering that gi of x, whose absolute value divided by the norm of wi, is the distance from the input point to the hyperplane, assuming that all wi have similar length. Thus assigns the point to the class among all gj of x greater than 0, to whose hyperplane the point is most distant. This is called a linear classifier, and geometrically it divides the feature space into k-convex decision regions. Ri, see figure 10.3. Figure 10.4, in a pairwise linear separation, there is a separate hyperplane for each pair of classes. For an input to be assigned to C1, it should be on the positive side of H12 and H13, which is the negative side of H31. We do not care for the value of H23. In this case, C1 is not linearly separable from other classes, but is pairwise linearly separable.